Imagine a world where B comes before A. How would you verify if a list of words is sorted correctly in such an alien language? That's the challenge in verifying an alien dictionary. You're given an array of strings, words, and a string, order, representing the alien alphabet. The task is to determine if the words array is lexicographically sorted according to the custom order. This means comparing words character by character, using the alien alphabet sequence to decide which character comes first. If two words are prefixes of each other, the shorter word should come first. A straightforward but inefficient approach would be to clone the input words, array, and then sort this copy using a custom comparison logic. This custom comparator would consult our alien alphabet to compare characters. After sorting, we'd simply compare the sorted copy with the original array element by element. If they are identical, the original array was sorted. This works but sorting an array of strings, where each comparison itself involves iterating through characters, leads to a time complexity of n log nl, where n is the number of words and l is the maximum length of a word. The space complexity is big O of n for the copy. The key insight for optimization is that to verify if an array is sorted, you only need to check *adjacent * elements. If every pair of adjacent words is correctly ordered, the entire array is sorted. We'll start by mapping each character in the alien order to its rank or position. We can use an array for this, where the index is derived from the character and the value is its rank. For example, if H is the first character in order, its rank is 0. Then we iterate through the words array, comparing each word W1 with the next word W2. For each pair, we compare characters at the same index, using our precomputed rank map. If we find a character in W1 that has a higher rank than the character at the same position in W2, we immediately know the array is not sorted and return false. If characters are equal, we move to the next. If we exhaust one word and haven't found a difference, the shorter word must be a prefix of the longer one. In this case, if W1 is longer than W2, it's not sorted, so we return false. If we successfully compare all adjacent pairs, we return true. Let's trace with words as hello, LeetCode, and order as HLapDef. First, we build our rank map. H gets rank 0, L gets rank 1, A rank 2, and so on. Now we compare hello and LeetCode. We compare H from hello and L from LeetCode. H has rank 0, L has rank 1. Since 0 is less than 1, hello comes before LeetCode according to our alien dictionary. This pair is correctly sorted. Since we found a difference and it was in the correct order, we move to the next pair if there were any. Here, there are no more pairs, so we've confirmed the entire array is sorted. If, for example, H and H were compared, we'd move to the next characters E and E, then L and E. If L had rank 1 and E had rank 4, then L is less than E, so the order is correct. If L had rank 4 and E had rank 1, it's incorrect. For the example words, hello, LeetCode, and the given order, the algorithm correctly determines that the array is sorted. This is because H comes before L in the alien alphabet, fulfilling the sorting condition. You'll spot this pattern when a problem asks you to verify sorting or order based on a custom rule. Anytime you need to compare elements using non-standard criteria, precomputing a rank or a mapping for those criteria is usually the first step to an efficient solution. The time complexity is O(n)L because we iterate through n words, and in the worst case compare up to L characters. Space complexity is big O of 1, constant time for our rank map, as the alphabet size is constant. This adjacent pair comparison is a powerful technique for verification problems. Try the next problem using this same pattern. Don't forget to like and subscribe for more DSA insights.